Right, well, welcome back. Today the plan is to do two topics, which are both in Chapter 8 of my book. One is implicit differentiation, and two is related rates. And these are very nice, actually the related rates is a nice application of implicit differentiation. So we've got to do that first. We've got to do the implicit differentiation, and then we'll use that in related rates. For those of you in Math 103, I'm also supposed to talk about some sort of parameterization and the chain rule, and that actually touches on a little bit of some way forward chapter in the book. I think it's 27. So I'm going to do that at the end after the video finishes, just to keep you guys up to speed. But then next semester we have to more or less do it all over again, and then I'll cover that part of the book. So, without further ado, let's talk about implicit differentiation. And section 8.1. All right. So, in order to motivate this, and there's actually remarkably little theory in this, it's more or less just a quick technique, and then it will be a whole series of examples. But in order to sort of motivate this, let's just compare these two expressions here. The first one says d dx of x squared, and the second says d dx of y squared. Well, we should interpret d dx of x squared as meaning how much does x squared change if we change x by a little bit? And we know that the answer is 2x. So any change to x will produce a change in that quantity squared of roughly 2 times the change, as long as the change is small. X squared, change in x, 2x. How about y squared, d dx of y squared? Is that just 2y? No. Here's what's going on. We are implicitly assuming, without even stating it, that y is a function of x. So y is some function of x. So I change x a little bit, and y changes, right? But then, of course, when y changes, y squared changes by some other amount. So what this is really saying is how much does y squared change when we change x? And it will turn out, well, actually, let's not even say turn out, we'll just do it. Let u equal y squared. So this is actually equal to du dx, because after all, u is y squared. Now by the chain rule, in slightly different letters, this is the same as du dy, dy dx. So there's the chain rule. Of course, we can come over here. Du dy is 2y. No problem there, no implicit differentiation. U is a function of y, it's y squared, so change of u, change of y, du dy is just 2y. So coming in here, du dy is 2y, dy dx is just dy dx. So just to summarize that chain of equations, I have shown that d dx of y squared is 2y dy dx. So it's not just 2y, which is what you might have thought it was. It's 2y dy dx. And as I described, it actually makes perfect sense. I change x a little bit, y changes by an amount. There's that dy dx there. I don't know what it is. It depends how y depends on it depends on how y is a function of x. But y doesn't just change, y squared changes, and we need that 2y as well, because we're not just changing y, we're changing y squared when we change x. Okay? So basically, the technique is then going to be to use the chain rule quite often. We might also have to use the product rule and the quotient rule, and I'll show you some examples of that. But basically, the real idea is that we can differentiate things that are not just functions of x directly, x squared. They can be implicit functions of x, like y squared. So here is a sort of nice, easy example to see what's going on. If I start off with x squared plus y squared equals 4, that's the equation of a circle centered at the origin of radius 2. Square root of 4. It's 2. Okay, so this is not a function. How do you differentiate it? So far, the best we could do would be to make y the subject, and you'd get y squared equals 4 minus x squared. Then you'd take a square root, and you'd have to decide whether you wanted the positive or the negative square root, and then you could differentiate. But the other option, now that we know implicit differentiation, is we can whack a d dx onto both sides. And of course, really that means we can d dx each individual term in a sum, because derivatives are cool that way. So the question is, what do we do with the result? This is a legitimate thing. Rather than square both sides or whatever, I'm going to d dx of both sides. And I get this valid equation here. So now we actually know what these things are. This is just 2x. We just calculated this above, and this is 2y dy dx. So what's the derivative of 4? Well, common mistake is to write 4, but it's not. 4 is constant. How much does 4 change when you change x? It doesn't change. 4 is always 4. So the change in 4 is 0. Derivative of a constant is 0. So that's a valid equation. Of course, since y was not the subject, it wasn't the subject of the original equation, it's too much to expect that dy dx should be already the subject of this equation. It's not an equation in dy dx. So all you have to do is rearrange, and in this case, I whack the 2x on the other side, and I divide by 2y, and you get minus x over y. So dy dx is equal to minus x over y. And this is another interesting thing. We're used to seeing dy dx equals 2x or cosine x cubed or something like that. This has got a y in it as well. So you don't just get a nice function of x. You get a function of x and y. And in this particular case, it's quite nice. If you take a point x, comma y on the curve, the equation of this line, that line has slope y over x, because its rise is y and the run is x. So we know from elementary coordinate geometry that the normal to this line, that's perpendicular, is actually the tangent to the circle, right? Because the tangent is perpendicular to the radius. That's simple geometry. And we know normal to this line has slope, which is the negative reciprocal of the original one, minus x over y. So actually, we already knew the answer that we got, namely, the slope is minus x over y. Let's just look at a specific point. Suppose I pick the point with angle pi over 6. So sine pi over 6 is the y-coordinate. Actually, let's do the x-coordinate first. The x-coordinate is cosine pi over 6 times 2, which is just 1. And the cosine pi over 6 is root 3. This is what I want. Consider the point root 3, comma 1 on the circle. Question is, what is the slope of that tangent right there? Well, if x is root 3 and y equals 1, we just plug it in and we see dy dx equals minus root 3. Okay, so that's a specific example of how to use the implicit differentiation. So basically, all that's left to say about this topic, apart from one little thing at the end, is just a whole bunch of examples. Okay? So I'm going to embark on, let's see, well, I'll do 2 or 3 examples. So before I start, does anyone have any questions? Everything is cool so far? All right. Well, I wonder if they repaired the board. Guess they did. That was lucky. Okay, consider this curve. 5 sine x plus 3 secant y equals y minus x squared plus 3. So the question is, what is the equation of tangent at the origin? What is the equation of that? Okay, this is an example where you can't really solve this for y. You cannot make y the subject of that equation. So you don't even have the option, as we did, of taking square roots or anything like that. It's got to be an implicit equation like this. So, first of all, I think it's a good idea to do a sanity check and make sure that the origin is actually on the curve. I say, what's the equation of the tangent at the origin? It'd be pretty nasty if we asked a trick question where the origin wasn't even on the curve, but, it's conceivable. Let's just check. When x equals 0 and y equals 0, the left-hand side is 5 sine 0 plus 3 secant 0. Of course, sine 0 is 0, secant 0 is 1. How do I know that? Because cosine of 0 is 1, and secant is just the reciprocal. So this is 5, 0, plus 3, 1, which equals 3. And clearly the right-hand side is 0 minus 0 squared plus 3. So that is the left-hand side. Therefore, origin is on the curve. This is not a function, necessarily. It might be, but I doubt that it is. I have no idea what the graph looks like. Haven't even thought about it. But nevertheless, whatever its graph looks like, I guarantee you it goes through the origin. Now, we need to find the equation of the tangent. So we've got to take this original equation and hit it with a d dx. So I'm going to have d dx. I'll write it out in gory detail. d dx of 5 sine x plus d dx of 3 secant y equals d dx of y minus d dx x squared plus d dx of 3. Okay, in reality, you may decide that you can just write this down straight away. We know the derivative of sine is cosine. This one we have to differentiate implicitly, so I'm going to come back to it. I just want to point out that we don't really have to differentiate y implicitly. It's already just dy dx, so just don't get confused about that. d dx of y, of course, is dy dx. This is just minus 2x, and the derivative of 3 is 3, right? No, it's 0. Be careful. Okay, so really the only issue is what to fill in right there for the derivative of secant y. And it's actually very similar to the one we did when we differentiated y squared. Let me come over here, set up a little working column here, and just say, well, let u equal secant y. So if we remember, the derivative du dy, the derivative of secant x with respect to x would be secant x tan x. So of course we're just changing life to y, secant y tan y. So now we can use the chain rule. We want to find out what d dx of secant y is. And of course this is just d dx of u, as in du dx. Let's just write it as du dx, which is itself du dy dx. And now we can use our above expression for du dy to write this as secant y tan y dy dx. So now that's our little working box. And we can fill this in. Oh, I left out a 3. How did I leave out that 3? Well, you know what? It doesn't matter. 3's go through. Probably I should have let u be 3 secant y. But it doesn't matter. As I say, the 3 can go through. And we can just do it in this order and write 3 secant y tan y dy dx equals this. So, okay, we took our original equation, we differentiated it, both sides with respect to x, and we get this expression. And dy dx's are on both sides. What we really need to do is find dy dx. Now, we could rearrange and make dy dx the subject. So there's two ways we can go from here. The first way is that we could throw all the dy dx stuff on the left-hand side so that we'd have, say, dy dx with a factor of 3 secant y tan y minus 1. You see, I'm going to throw that dy dx on the other side and have a minus 1. And then, of course, I'm going to throw all the non-dy dx stuff on the other side. I get minus 2x minus 5 cosine x. And so I could actually just divide by this quantity here in the parentheses and get a nice expression for dy dx. Minus 2x minus 5 cosine x all over 3 secant y tan y minus 1, unless I made a mistake. Okay, so that's the general formula for dy dx. But it's actually, all we really need is what happens when x equals 0 and y equals 0. So, because we're looking for the tangent at the origin. So dy dx is equal to, well, it's 0 minus 5 times 1, so it's minus 5. We already discussed that secant of 0 is 1, but actually tan 0 is 1, so that goes away. And you get that the derivative at the origin is 5. So we still have to find the equation of this tangent. What do we know about it? We know it goes through the origin, and it has slope 5. Well, we don't even need the point-slope form. The tangent line is y equals 5x. We can just use the point-intercept form because we know the y-intercept is 0. So there it is, y equals 5x. So that's one possibility. Another possibility, maybe we can just pan up to this original equation here, 5 cosine x. So it's this one right here. See, we found a nice equation for, well, it's not really a very nice equation, but it's an equation involving, dy dx's. You could substitute at that point. So if you substitute x equals 0 and y equals 0 earlier, so I'm just going to rewrite the equation for the sake of the video. I've decided to just rewrite it. 5 cosine x plus 3 secant y tan y dy dx is equal to minus 2x, equals dy dx minus 2x. Okay, so there it is again. Didn't need to pan, but never mind. If you just put this in directly, you will get 5, and then this is all going, because tan of 0 is 0, so it equals dy dx minus 2, 0. So actually, dy dx equals 5 automatically. It doesn't take as long. So unless you actually need a general expression for dy dx, as opposed to its value at a particular point, then it's probably better to do the second method. Just differentiate the thing, find out, simplify it down to this sort of equation, but don't bother finding dy dx as the subject of the equation. Don't solve for dy dx. Just plug it in first and then solve for dy dx. It'll be a little quicker. Yeah, question?
What is that dy dx on its own?
That means how y changes when x changes. So you see, if you look back at the original equation, it's right at the top of this board here. Right? Y and x are related in a certain manner. Right? Now, it's not an easy to understand manner because if you give me what x is, I can't in general find y. But nevertheless, there's some 1 or 2 or some small number of y's that will work. Maybe it's infinite, but they're not all on top of each other. Just like sine, of course. These things have trig functions, so it may be infinitely many solutions. I don't know. I'd have to think about it. But see, y and x are related. So dy dx equals 5 means however the curve looks when it's going through the origin. I have no idea what the curve looks like. I mean, it could be just some horrible hodgepodge of thing. But I know when it goes through the origin, the slope there is 5. Yeah. So when I'm over here, and I'm going to plug x equals 0 and y equals 0. 5 cosine 0 is 5. 3 times secant 0 is 1. Tan of 0 is 0. So that kills off that term. Equals dy dx minus 2 times 0. So I didn't actually ignore anything. That dy dx is this dy dx here. I know I didn't repeat the question, but hopefully it was clear from the answer. So yeah, I didn't just ignore it. In fact, this one is the one that went away, but only because tan of 0 was 0. All right. Any other questions about that example? As I say, I recommend method 2, because I think it's just a little easier. But sometimes the question would be, find a general formula for dy dx, or just find dy dx. And in that case, you want to, you have to do method 1, because there's nothing to substitute. You do have to solve for dy dx. All right, let's look at a couple other examples. Then we'll talk about the second derivative, but then we have to move on to related rates. All right. Let's jump ahead to, I think I'll jump ahead to the second example. So there's another example in Chapter 8 in Section 8.1.1 in between the first one that I did and this one I'm going to do now. But this one's a tough one, and I think if we can do this one, we should be able to do any. So I have this diabolical equation, x minus y cosine quantity y over x to the fourth equals pi plus 1. And I'd like to know the equation of the tangent line at 1 pi to this curve, 1 comma pi. Now, this is morally exactly the same question as the one we just did. It's just a different defining equation and a different point. So the methodology is the same. The difference is that we're going to have to use the quotient rule and the product rule, actually, as we go along, since we have a product here and a quotient inside there. So this is sort of about as nasty as you might expect from one of these implicit differentiation problems, except for the second derivative, which I will talk about after doing this. Anyway, again, here's the reality check. Check. When x equals 1 and y equals pi, the left-hand side is x minus y cosine y over x to the fourth. I just replaced y by pi and x by 1. This is cosine of pi. Cosine of pi is negative 1. You remember, you need to know all your cosines. Just draw a graph of cosine if you don't believe me. There it is. Cosine of pi is minus 1. Okay, so this is 1 minus pi times minus 1. So it actually equals 1 plus pi, which is nicely the same as the right-hand side. So yes, 1 comma pi is on the curve. Strictly speaking, if you skipped everything up to that point, you would probably still get full credit, at least on a Princeton exam. I don't know about anyone else watching this from anywhere, but the fact is, I think it's good to spend a few seconds and just check that it's on the curve, just in case the dastardly trick question is, oh, well, actually, it's not on the curve, so there is no tangent. In any case, we now need to come back to the original equation and do a ddx. And, frankly, I don't even need to write dx. I can just differentiate in my head the derivative of x is 1. However, in my head, I cannot differentiate y cosine y over x to the fourth implicitly, so I will just give that up for a moment. On the other hand, the derivative on the right, pi plus 1, I'm afraid, is still a constant, even if it was pi squared. If this was pi squared plus 1, do not fall into the trap of thinking the derivative of pi squared is 2 pi. I've seen it. It's not true. Pi squared is as much of a constant as is pi plus 1. The derivative of any constant is 0. So, we need to do quite a lot of work on this quantity. So, what is this quantity? This, first and foremost, is a product. It's a product of y, and it's a product of cosine y over x to the fourth. So, I am going to let, I've got to take quite a lot of working here. I'm going to let s be this pesky quantity, y cosine y over x to the fourth, so that all I want to do is differentiate s. I'm going to let this be v. Let v be cosine y over x to the fourth. So s is equal to yv. Now I'm going to use the product rule to find ds dx. According to the product rule, it's v dy dx plus y dv dx. Of course, normally you write uv, and you could replace y by u, but then you just change it back to y. So I don't know. I think we should be able to cope with the product rule with a y instead of a u. Anyway, this is not too bad. It's cosine y over x to the fourth dy dx, which is as much as we could possibly expect to be simplified, plus y d dx of this quantity v. Ugh. Well, we still need to differentiate this implicitly, but at least there's no y out the front. Now it's just cosine y over x to the fourth. So somehow, I've got to backtrack my steps. I'm going to write cosine y over x to the fourth dy dx plus y times blank, and I'm going to fill in that blank in a short while. And that will allow me to come back and fill in the first one. So you've got to keep your working quite well understood here. So in any case, the next thing I want to do is find, I still need to find d dx of cosine y over x to the fourth. Well, how do we deal with that? What do I want to call it? I would like to call this quantity v. Well, I've already done that. And I'd like to think of v as cosine of t. I need to pull out another variable. Let's say t, where t equals y over x to the fourth. See, we're gradually worming our way down into the middle. So dv dx is dv dt times dt dx. That's the chain rule. So we've used the product rule, now we're using the chain rule. Well, dv dt, v is cosine of t. So dv dt is negative sine of t. So let's keep a clear head here. Move over to here, negative sine t times dt dx. And dt dx, just to put this in perspective, is y over x to the fourth. Now, of course, we've used the chain rule, so we'd better put t back to y over x to the fourth. It seems like we're taking forever. But every time we make it a little simpler. This time we've gotten rid of the cosine. We started here with a cosine. That's come out as a negative sine. And now we just have to differentiate the interior part. So, I'm going to leave a blank. And for the last time, I just need to find one more thing. I told you this was nasty. This is a quotient of two things, y and x to the fourth. So let's let capital U, I've already used little v, so I'm just going to let capital U equals y, capital V equals x to the fourth. Maybe I don't even need capital U, but what the hell. So this is equal to, we call this t actually. Y over x to the fourth was t, and t is u over v. It's y over x to the fourth. So by the quotient rule, this is capital V u dx minus u dv dx all over v squared. I'm getting exhausted, but we're almost there. V is x to the fourth. Du dx is just dy dx. U is y. dv dx is 4x cubed. And that's all over v squared, which is x to the 8th. And I guess we should simplify this to 1 over x to the 4th dy dx minus 4y over x to the 5th. Oh man, what a pain. Okay. This has to be written in here. That whole mess has to be written all the way up here. So I'm going to pull the minus in here. I hope I didn't make a mistake. And finally, all this has to be pulled into this equation here. 1 minus, well, d dx of all that crap is equal to all this stuff here. And I'll just write it out again. Cosine y over x to the 4th dy dx. It's much easier on paper because you don't have to look all the way over there. I hope I'm copying out this whole thing correctly. Ugh. 1 over x to the 4th dy dx minus 4y over x to the 5th. Okay. Now, all this equals 0. Just like it does on the previous equation. Pause for breath. Now, put x equals 1, y equals pi, because the question said, what is the tangent at 1 comma pi? And I will get 1 minus cosine pi dy dx minus, now you know what? I could go y sine pi times this. I don't even need to substitute in that crap. I think so little of it that I'm even willing to write crap. Actually, you probably shouldn't do that on an exam. That's just bad. Let's just use stuff. I don't know. Some people don't like this coarse language. In any case, the reason I can put stuff is that sine pi is 0. So I'm sort of lucky here. I don't even have to work out what that stuff is. This is just 0. So all that goes away. And just working down here, this equation, given that cosine of pi is actually minus 1, it all works out to just 1 plus dy dx equals 0. So after all that, dy dx is just equal to minus 1. How do you like that? Does that agree with what I found in the book? Bloody well hope so. I don't think I wrote it down. Nope. So either I made a mistake there or I made a mistake here. But in any case, there's the slope of the tangent. The tangent goes through 1 pi, has slope minus 1, so we can just write down its equation as y minus pi is equal to minus 1 outside of x minus 1. Or if you prefer, y is equal to minus x plus 1 plus pi. All right, so that's a pretty hard and messy and involved problem. But as I said, if you can keep all these facts straight in your head or on the page, then you should be able to have no problem with any implicit differentiation problem. Okay, any questions about that monstrosity? I've seen things as hard as this on Princeton exams. I say hard, what I really mean is involved, messy, time-consuming. So just make sure you can do them. Okay, the only other thing I want to show you about implicit differentiation before moving on to related rates is how to deal with the second derivative. Occasionally, you might want to find that. So it's nothing to be scared of, afraid of, but it helps if you've seen it. So let's see it. Here's another one of these classic sort of bizarre function or relations. 2y plus sine y equals x squared over pi plus 1. And the question I want to ask is, find the value of the second derivative, d2y dx squared, at the point pi over 2. That's the question. Now, you may actually be able to solve this for x by, subtract 1, multiply by pi, take the square root. But let's do it implicitly. Let's do it implicitly. Even if you could solve for x, which you can, it's not easy to get the second derivative. So, let's, first of all, take a d dx of all this. Well, what do we get? We get 2 dy dx plus, well, look, we can use the chain rule. We can let u be sine y, but we see how this goes. You just get the derivative with respect to y, cosine y, and multiply by dy dx. So check that with the chain rule if you want to. But by now, we might actually be able to do it in our heads. The derivative of x squared is 2x. So we've got the factor of pi down there, and the derivative of 1 is nothing. So there is the equation for dy dx. Now, here's the thing. We could solve for dy dx and then differentiate implicitly. But maybe even the simpler way is to, again, take d dx of all of this. See, we need a second derivative, so we're going to have to differentiate twice. The question is, do you solve for dy dx and then differentiate? Well, you could, but it's actually probably easier to re-differentiate implicitly. So let's see how it works. 2 comes out. The derivative of dy dx is just the second derivative. We have to be a little careful here. When we differentiate this, we're not just differentiating either of these terms. We're going to have to use the product rule. So in order to understand this, let's just write down the derivative of cosine y times dy dx equals, and the derivative of 2 over pi x is just 2 over pi. Right, so we need to tackle this thing here. And so let me take another set of working here. Let's let u equal cosine y and let v equal dy dx. And we really want to find derivative of uv. So d dx of uv is v du dx plus u dv dx. Well, v, if you look, just got to really keep these things clear. V is dy dx. What is du dx? Well, unfortunately, u is already cosine y. So we're going to have another implicit differentiation, which we'll do in a second. On the other hand, u is cosine y. And what is dv dx? Let's just write this down. dv dx is the derivative of dy dx. And of course, the derivative of the derivative is the second derivative once again. So this dv dx here becomes the second derivative, d2y dx squared. Okay, we're almost done. We need to still find d dx of cosine of y? Well, we do the same little trick. You could write it out as the chain rule. Or you could just say, look, the derivative of cosine is minus sine, so I'll put minus sine, but it's not just x, it's y, so I need to multiply by dy dx. And the other term is as before. So I'm going to come back and insert this over here. 2 times the second derivative plus junk. What is the junk? I simply need to copy it over here. Let's just focus for a second on this first term. We have a minus sine y, we have a dy dx, and another dy dx as a factor. So if we come back over here and write that down as minus sine y times dy dx all squared, because we have two factors of dy dx. And then I'm just going to copy the other factor, cosine y d2y dx squared, and that is equal to 2 over pi. So there's the equation. Now, I want to stress something here. This is not the same thing as this. The second one, d2y dx squared, is the second derivative. It's the derivative of the derivative. But this is dy dx, all squared. That's the square of the derivative. They are, believe it or not, different things. They are completely different things. There's really no relation between them. They just look similar. So beware, dy dx times dy dx is dy dx all squared. It's not the same thing as d2y dx squared. So, word of caution. In any case, what we have now is an equation relating the second derivative and y and the first derivative. So, I need to find the value of the first derivative as well in order to use this equation. So, having done all these derivatives, we now are ready to let x equals pi and y equals pi over 2. This comes from the question, if you look way back up over there, the point we care about is pi, comma, pi over 2. We haven't used that point yet. So I'm going to use all three equations. This might be a little hard for the video, so maybe if you guys look back, I'll call this equation A. That's the first equation. I'll call this one B. That's the differentiated equation. And I'll call this one C. So that's the simplified one. So maybe that's the simplified second derivative equation. Let's just plug this into A. This is actually just a check that this point is on the curve. We'll have 2y, which is 2 pi over 2, plus sine pi over 2, equals x squared. That's pi squared over pi plus 1. Let's just put a question mark because we don't know if that's true. The left-hand side is pi. Sine pi over 2 is 1. And that is indeed pi plus 1. Yes. So the reality check, the point lies on the curve. Now we go to the derivative equation. And we have 2 dy dx. I'm just copying from equation B above. Plus cosine y is pi over 2. dy dx is equal to 2x over pi. But x, of course, is pi. So I've just taken equation B from above, and I have replaced y by pi over 2, and I've replaced x by pi. What do I get? Well, cosine pi over 2 is 0. See why you've got to know your trig there. So that goes away. And we have found that 2 dy dx equals 2. So this means when x equals pi and y equals pi over 2, dy dx is 1. 2 divided by 2 is 1. But we're not done because we need the second derivative. So now I have to come over to equation C and plug in x equals pi, y equals pi over 2, and dy dx is 1. That's what we just found out. And if we plug in those quantities into this equation C, we get 2 d2y dx squared plus minus sine of pi over 2 times dy dx all squared, which is 1 squared, plus cosine pi over 2 times d2y dx squared. All that equals the right-hand side, which is 2 over pi. So that is equation C, specialized to the point when all three of these things are true. Now, once again, we use the fact that cosine pi over 2 is 0, sine pi over 2 is 1, and if you rearrange this equation, you will get 2 d2y dx squared minus 1 equals 2 pi. So d2y dx squared works out to be 1/2 plus 1 over pi. Is that what I got in my book? Probably not. You know what? I didn't even write it down. Let's just see how good I am on the board. That's correct. Amazing. I worked out the problem twice and got the same answer. Must be right. Okay, so I guess the moral of the story is here, do all your derivatives first and then substitute. That's going to be the moral when we do related rates in a few seconds. That's all I really want to say about implicit differentiation, in fact, unless you have any questions. One quick question. Why is the 2 there or the 2 here? Where do you think the question is why is it 2 instead of 0, but where should the 0 be? This big 2 here? That 2 has just propagated its way all the way down. The original equation was 2y all the way at the top there. So the derivative was 2 dy dx, and the derivative of that was 2 d2y dx squared. It has nothing to do with the second derivative. It's just the 2 was a constant that just carried on. Another question up the back there. Okay, so the question is, from equation B up there, if we can just focus on the second line up there, we have equation B. Why not make dy dx the subject, or solve for dy dx, and then differentiate? And you could do that too. I did mention this. Let me just try to go from B. If I do make dy dx the subject, or solve for dy dx, you get something like this, 2 over pi x divided by 2 plus cosine y. That is another way of writing B. And then you could differentiate both sides. You'll get d2y dx squared there, and then you'll have to differentiate this implicitly, and you'll use the quotient rule, where we use the product rule. And that's a totally legitimate way of doing it, absolutely. And it would be a good exercise, in fact, for everyone to try differentiating that, and then plug it in and see if you get the same value of 1/2 plus 1 over pi. You will still, however, need to find dy dx at that point, because the formula, this formula, when you differentiate this, will involve a dy dx, because it's implicit. Yep, you still have to do this step, which is just a check, so maybe you don't have to do it anyway, but you definitely have to do that step and find that dy dx equals 1. But then you will take your differentiated equation, plug those three values in, pi, pi over 2, and 1, and you will get the value for d2y dx squared, which should be the same as the one that I got there. And if it isn't, I want to know about it. It will be the same if you don't make a mistake. Or if I didn't make the same mistake twice, which is entirely possible too. Any other questions about this? It's about as hard as it gets. Just want to point that out. Implicit differentiation anyway. All right. Well, that's all very well and good. Let's do some word problems. Well, we had to do word problems eventually. We haven't actually done any. But now, what we're going to try to do, I will tell you a little bit as I'm erasing the board, is we're going to do some word problems that involve derivatives. And in fact, they're all going to involve quantities that change over time. So these are not static quantities. They're quantities that change. And of course, a lot of things change over time. Speed is the change of distance with time, or position. I guess velocity is the change in displacement. So whenever anything moves, it's changing. So it has a rate. But there are other things that can change. Volumes of balloons, heights of objects, parachutes, all that sort of stuff. So it's about time we did some word problems. Okay. So in order to talk about related rates, which is in section 8.2 of my book, in order to talk about this, I need to understand what do I mean by related and what do I mean by rates. That seems like a good place to start, right? So here's the idea. We have quantities that are somehow related, meaning there is an equation that relates them. Well, we've seen when we did implicit differentiation, we had quantities x and y, and they're related by some equation. So that's what I mean by related. It's not a family thing. They're just related mathematically. Now, rates. What is the rate of something? Rate is a code word for DDT. Whenever you see rate or rate of change, you should think DDT, change with respect to time. It's rate, how fast is something changing? With respect to what? With respect to time. That's what I mean by fast, or change for that matter. Okay, so this means if you have a quantity Q, so the rate of change of Q, or the rate of Q for short, is dQ dt. Now no one is going to tell this to you. The problem will say, what is the rate of so-and-so? It is up to you to remember that rate is ddt. So drum that into your brain. Rate, ddt. Okay. So having said that, we're going to look at problems which involve calculating various rates. And more or less, they have the same format. And I'm going to write down a 4-step method for solving these types of problems. Really, there's a lot within each step. And you do have to do a lot of practice. There's a whole variety of problems. I'm going to write down these 4 steps, and then I'm going to look at 3 problems. And I'm going to explain how the 4 steps work in each problem. So this is the basic method for solving one of these problems. I haven't even told you any of the problems yet. I'll just tell you the method first, and then we'll see how to use it. So step 1 has a few little parts to it. Basically, the idea is read the question. Okay, well, that's pretty obvious. You've got to do that all the time, but really read the question. It'll have more words than normal. It might be all words with a few numbers. But the point is you have to identify changing quantities. And there will be at least 2, or else the thing isn't very interesting. Now, some things change and some things don't. Right? If they say a tower is 30 feet high, it's not a very tall tower, but whatever. A tower is 30 feet high, someone walks, the shadow changes, then 30, the height of the tower is not changing. Right? Unless the question then says the tower is built on quicksand and it sinks at a rate of... But basically, 30 would be the quantity for the tower. So that's not a changing quantity. But you've got to sort of say, okay, play out the scene in your mind and see what quantities change. So you've got to identify them, and you should actually make variables for them. So you should write a statement like, let blah be the word, let Q be the so-and-so, etc., one for each variable. It's a good idea when you're solving a word problem to translate it into math by using some words. Then do math, and at the end we'll translate it back into words. Okay, now, one of these quantities is going to be the one you need to find the rate of. So the question says, find rate of something. So all I want you to do is identify that quantity as the special one. This is the special quantity. Out of all the quantities, and there might be only two, most of the time there are only two, but one of them is the one you want to find the rate of. So make a note that that is the one we want the rate of. Okay. So sort of step one is the preparatory work, just to identify variables and just get a feel for the problem. Step two is write an equation, or equations if there are more than two quantities, that relate the quantities, or write equations relating the quantities. So the idea is that when one of them changes, the other one or the other ones have got to change as well. They have to be related. You can't possibly solve the problem if one of them is the flap of a butterfly's wings and the other one is the power of a hurricane. Well, maybe you can. But basically the quantities have to be related. And you should write down an equation relating. Step three is to go d dt of both sides of every equation. So that's basically, i.e., differentiate all equations implicitly with respect to t. WRT is with respect to t. So we're going to whack every equation with a DDT, both sides. If we only have one equation, we just do that one. But if we have two or more, we do them individually. What this will give you is equations relating the rates of the quantities. Not just the quantities, but relating the rates, hence related rates. Finally, solve simultaneously for the rate you want. How do you know which rate you want? In step one, we identified the one that we want the rate of, Q. So here we want to find Q, dQ, dt. So I actually should say, when I say solve simultaneously, I've missed a word or two words. Substitute. Substitute, then solve. Okay, so the point is that the substitution has to happen after the differentiation. Any variable quantities we're going to plug in are going to be after we differentiate. Again, this will make more sense when I look at an example, but I want to sort of lay the groundwork. The only other thing that's left is then summarize in words. Okay, so there's a method for solving problems of a type that we haven't even done any examples of yet. So rather than take any questions, I'd like to just do one fairly simple example, show you how all this works in that case, and then if there are any questions, we'll do that. Okay. We have a bit of an influx at the 1 hour mark. Good. So here's the method for doing related rates. Here is a problem that you can find in 8.2.1 of the book, and it is a fairly straightforward example. You have a perfectly spherical balloon, which is inflated by some sort of air pump or some strong person, and it's a constant rate of air. Air goes in at 12 pi inches cubed per second. So that's about 36 inches cubed per second. That's quite a lot. That's quite a lot. This balloon's going to expand fairly quickly. Okay, but it's a constant rate of 12 pi, so it's some pump that's just pumping the same volume of air in every second. And the question is, what is the rate of change of radius and there's two parts. Part A, when the radius is 2 inches, and part B is instead when the volume is 36 pi cubic inches. So there's two separate parts. How fast is the radius changing? Well, see, the thing is, you should understand that the volume is changing at a constant rate. But that does not mean that the radius changes at a constant rate. For example, it starts off at 0, say. It's a tiny little balloon, microscopic. You blow some air in, it grows very quickly at first, right? It sort of goes like this, and then it slows down. Because volume is not the same thing as radius. If I take a sphere of radius 1 and a sphere of radius 2, the second one has 8 times the volume of the first one. So that's no good. So we're going to have to do some work. What are the relevant quantities here? Let's look at step 1. It says, identify the changing quantities. Well, we've really only got 2 relevant quantities here. We've got the radius and the volume. So the quantities are radius, so let radius be r in inches, and let the volume be v in inches cubed. It's a good idea to put the units down there so we get them right at the end. Okay, which is the one that we're interested in the rate of change? Well, the question says, what is the rate of change of the radius? So this is the one we're going to want. We want the rate of this. All right. That's all that we need to do with step 1. Step 2 is we need an equation relating v and r. Well, this isn't just any old balloon. It's a spherical balloon. And we should know the formula for the volume of a spherical, or of a sphere, in terms of the radius. This one you might just have to commit to memory. V is 4/3 pi r cubed. It's, at Princeton at least, they don't really give this to you. They expect you to remember the volumes and surface areas of spheres and cones and cubes and stuff like that. You don't need to know about frustum of a cone or whatever. Just the really common things like spheres. So there is the equation that relates v and r, but it does not relate their rates. In order to relate their rates, you need to take a d dt of both sides of this implicitly. Well, if you differentiate v with respect to t, you mercifully just get dv dt. 4/3 pi is just a constant, and then we're going to have d dt of r cubed. Now, if this was just t cubed, the answer would be, that derivative would be 3t squared. But it is not t, it is r cubed. So the chain rule, which you can write out in gory detail if you like, I propose to do what I've been doing recently and just sort of understand what's going on. When I change r cubed, that would be like 3r squared, but then r also changes, and I need to correct for that. And I get the d dt of r cubed is 3r squared dr dt. Okay, so let's rewrite that. So we have shown that dv dt is, well, we can cancel out the 3's here. So it just works out as 4 pi r squared dr dt. Let's pause for a moment, take a look at that while I get some more space over here. Look at that 4 pi r squared. That's actually the surface area of the sphere. It's a bit of a coincidence. Maybe. Maybe not. Anyway, let's not speculate philosophically. Let's actually solve the problem. Okay, so we have shown at the end of step 3 and I'll just rewrite this again so we can all see it. dv dt is 4 pi r squared dr dt. And there is an equation that relates the rates. Okay. So what is it that we're trying to find? Well, we're trying to find dr dt, right? Remember, we were looking for the rate of change of the radius, which is dr dt. Radius is r, so the rate of change is dr dt. Remember, rate d dt. So we better know what dv dt is. Well, the question says air goes in at 12 pi inches cubed per second. So dv dt is just 12 pi, because the balloon is increasing by 12 pi in volume every second. And we get this equation, which we could actually simplify a little bit. 3 equals r squared dr dt. I'll just leave it like that. Actually, I won't. I'll change my mind. Dr dt is 3 over r squared. That's a general sort of equation for dr dt. Now, notice that although dv dt is constant, it's 12 pi, dr dt is not constant. Dr dt depends on what r is. The change in the radius depends on what the radius actually is. Put another way, the radius is changing at a different rate throughout the life. Remember, when you first start, it explodes up very quickly, but then it slows down. Well, this quantity is actually infinite when r equals 0. And it's very, very large when r is tiny. But when r gets larger, it gets smaller and smaller, so the rate of increase of r is smaller the larger the balloon is. So it makes sense. Anyway, let's solve both parts of the problem. So we're actually in step 4 already at this point, which said substitute in and solve simultaneously. In part A, we know r equals 2. So dr dt, so let's say when r equals 2, dr dt is 3 over 2 squared, which is 3/4. So I said you should write a sentence. Rate of change of radius is 3/4 inches per second. Right? The radius is in inches, so you've got to put a unit here. It's inches per second when the radius equals 2 inches. So at that particular moment of time, the rate of change, dr dt, is 3/4 inches a second. That's how fast it's increasing at that point, right at that instant of time. Now, I did say something about substitution and how you've got to do it after you differentiate. Just to put this in perspective, suppose we did something silly like this. Here's our alternate bad window here. V equals 4/3 pi r squared, r cubed rather. Well, when r equals 2, V equals 4/3 pi times 8, which is 32 pi over 3. So you might think, oh, all we have to do is differentiate this. So you would get dv dt equals 0. Well, that can't be right. I mean, we've reached a dead end. What did I do wrong? What I did wrong was I said, here's the equation relating the quantities. I plugged in the r, and I got the v, and I've just frozen time. There's no time anymore. All I've done is said, okay, r is always 2. So it's now a static balloon of radius 2. Its volume is 32 pi over 3 cubic inches. But that's it. That's how it always is. So of course, dv dt is 0. If you substitute first, the derivative is always going to be 0, because the derivative of a constant is 0. So that's no good. What we really need to do is examine what the change is first, and then take a snapshot in the context of a change. So that means you have to differentiate first, then substitute. So 3 and 4 are not reversible. Steps 3 and 4 have to be done in that order. Anyway, I still have to do part B. Well, part B says when the volume is 36 pi inches cubed, so V is 36 pi, well, the formula that we have is dr dt is 3 over r squared. But it does not say V, it says r. So we need to come back to the original equation, which was V is 4/3 pi r cubed, And we need to plug in 36 pi into that. And you will get 36 pi equals 4/3 pi r cubed. And if you solve for this, you'll get that the pi's cancel out. You'll get r cubed is 27. So r equals 3. And then you can plug that into here and see that dr dt is 3/3 squared, which is 1/3 rather. So at that moment, the rate of change of the radius, I'm going to use some abbreviations here, is 1/3 inches cubed, inches per second rather, when the volume is 36 pi inches cubed. All right, so there is the method in terms of a particularly straightforward problem. Any questions about the method or the problem? Question here. I got dv dt, yeah, 4 pi r squared dr dt. You could plug in r equals 2 and dv dt is 12 pi, as I did. And that would be substituting both things at once. But then for the second part of the problem, you would have to unwind that r equals 2 and actually put r equals 3 instead. But dv dt was still 12 pi. So I kind of put it in, I put the 12 pi in first because it was true for both parts of the problem. And then I got a formula that was sort of simpler and I could use it. But what you suggest is fine. You can do the substitutions in any order as long as you do the differentiation first. Are there any other questions? Okay, well, I have another question. Here it is. I've got a house. It looks like this. It's more of a shack, really. And there are two cars, A and B. And they're pretty bad cars. B is being driven by my mother. So she is driving towards my house. And, in fact, she's going at 45 miles an hour towards my house. Whereas A is being driven by my mother-in-law. So she is driving away from my house at a speed of 55 miles an hour. She's in a bit of a hurry to get away from me. No, we get on really well. We get on really well. This is just an example. In any case, get the picture. These things are going like this. What I'm interested in is the rate of change of the distance between the two cars. So what is the rate of change of the distance between the cars when, and I need to tell you when, A is 21 miles north of the house and B is 28 miles east of the house. And just in case you think I'm trying to be tricky, I'm not. North is this way. Okay, so A is not actually driving up a brick wall here. I just don't know how to draw the top of a car. So it's a schematic diagram, damn it. Okay, so here we go. Now, here is what I think would be a mistake. Oh, A is 21, B is 28. That's a mistake. As soon as you write that in, you have taken a snapshot. You have fixed time. You are not allowing these things to change. So, do not plug that in. Instead, call them something, say A and B. Because unless they are actually not changing, you do not want to mark them with the numbers on the diagram. If they're changing, you need to give them variable names. So step 1 is going to be let A be the distance from car A to the house, H, in miles. And let B be the distance from B to the house in miles. So those are two reasonable quantities that are actually genuinely changing. But there's another quantity that we need to identify, because the question says, what is the rate of change of the distance between the cars? So we'd better call that something C, say. So let C be the distance between the cars. And again, everything is in miles. Okay? No one is going to hold your hand and do this for you. You have to do it yourself. Admittedly, I didn't write out the question properly. I needed a couple more sentences that says, car A is moving away at 55 miles an hour, car B is moving towards at 45 miles an hour. I did write it out properly in the book. But the point is that, you know, there's no diagram that necessarily even needs to be provided, and certainly no one is going to tell you what to call the variables. If you're lucky, maybe they'll give you a diagram. And the variables, there's no reason for them to. So you have to take the initiative. You can call them whatever you like. I chose A, B, C because the cars are A and B, and hell, C is the next letter. But you can call them whatever you want. Okay, so that's step 1. This is the quantity that I care about. I want the rate of change of C. Okay, so moving on to step 2, I need a quantity involving A, B, and C. Not a quantity, rather, an equation relating A, B, and C. I can only think of one, and it's Pythagoras' theorem. So you'll have to agree that A squared plus B squared is C squared. That's Pythagoras' theorem. All right, so that's the only equation that I can think of. So we might as well take that equation and hit it with the ddt. Well, if you differentiate A squared implicitly, by now we know the derivative of A squared is 2A times the derivative of A. So this is 2A dA dt. Derivative of B squared is 2B times dB dt. And wouldn't you know, the derivative of C squared is 2C times dC dt. Okay, you could use the chain rule to do any one of those, but I hope once you've done one of them in gory detail, you will realize that you could get the other two simply by switching out the variable A to either B or C. In any case, we can, in fact, cancel out the 2's, but we are still left with A dA dt plus B dB dt equals C dC dt. Now, what do we actually know? Step 4, I'll come over here, we are now allowed to substitute. And now we can put in when A equals 21, because that was the data, B equals 28, so we know that particular thing, and also always we know dA dt is what? What is dA dt? Look at the diagram. That's the rate that A is changing. Well, as your car A moves away, the speed is 55. So dA dt is always 55, unless the driver, my mother-in-law, accelerates. But I didn't say that. I just said constant speed. So, in fact, at every time dA dt is 55. And what is dB dt? Well, that car is going at 45. So you might think dB dt is 45. But this is wrong. B is actually decreasing, because this car is going towards the house. So this distance is getting shorter. So this means that actually you need to put a minus. dB dt is minus, or negative 45. Okay. We are almost done. If you look at this equation, we say we now know A, we know dA dt, we know B, we know dB dt, we want dC dt. But we still need to find C. So how are we going to do that? Well, we need to go back to the original equation. Now I will fix this at 21, 28, and I can use Pythagoras' theorem to see that C squared is 21 squared plus 28 squared. That's sort of a hard thing to solve. But actually, if you pull out a factor of 7 squared, you see it's 7 squared times 3 squared plus 4 squared, which is actually 7 squared times 5 squared. So this means that C is actually equal to 7 times 5, which is 35. I didn't need a calculator to do that. Does that even come out on the video? Is the lectern in the way? Oh, good. Okay, so we have A is 21, we have B is 28, dA dt is 55, dB dt is minus 45, and C is 35. So I come back here in the equation and I do a grand set of replacements. A, 21, dA dt, 55, plus B. B is 28, dB dt, minus 45. Equals C, 35. dC dt is the unknown. Everything else is unknown, is known. And now we have to divide both sides by 35. This actually works out pretty nicely because I can divide this by 7 and this by 5 to get me 3 times 11. And I can divide this by 7 and this by 5, and this is equal to dC dt. I'm running out of room. One always hopes one can solve the problem in the space provided, but maybe we can cogitate on what we've done so far. And we're almost done with this problem. All right, so where are we at? We just have to solve this little, or we just have to do a basic calculation. And dC dt equals, I'm just going to read it, it's 33 minus 36, unless I made a mistake. So it's minus 3. Is that what I think it is? It's probably what I think it is. It is. dC dt is minus 3. Well, we better write this in words. First of all, C was the distance between the cars. dC dt is the rate. So at the moment of interest, it's too complicated to describe, but it's basically when one car is 21 and the other one's 28 miles away. Rate of change of distance equals minus 3 miles per hour. Well, there is something. This is not a very satisfactory way of writing it. I mean, it's correct, but maybe we could say cars are, well, first of all, are they getting closer together or are they getting further apart? C is the distance between them. Is it decreasing or increasing? It's decreasing because it's negative, so that means the cars are getting closer together. So cars are getting, i.e., cars are getting closer together at 3 miles per hour, which you could also write as mph. Now, it sort of seems a little weird, right? Here's two cars. This one's going like this. This one's going like this. How are they getting closer together? Well, this one's actually going faster than this one. So they're sort of going like this. Right? So actually at that instant of time, even though this one's going away, this one's going towards, sort of more towards, more quickly. So the distance between them is decreasing. Eventually it'll start increasing. But at that moment, it's decreasing. So you've got, the moral of this is, first of all, this example has 3 quantities, and you only have one equation. Doesn't matter, you can still solve, because you have so many rates. And second of all, there are 2 places where negatives came up. One was that we had to make dB dt negative because the car was getting closer to the house. And second, we had to interpret the -3 answer here as negative. Well, it is negative. We had to interpret what it meant to be negative. Again, things getting closer together instead of further apart. Okay, so that's a sort of slightly different flavor and slightly harder example. So do we have any other questions about this example? All right, let's do a harder one. This will be the last one that I do. Then maybe I will have some time left over. I'll either take your questions about rates. In fact, that's what I will do. But if you don't have any, I'll talk about parameters, even if we are getting on video. And it's not until chapter 27 in the book. Talk about being out of sequence. Okay, so but first I want to do the example from 8.2.2, a harder example. Okay, you have an absolutely massive cone propped up on the point. I don't know why, I guess some people do this, but whatever. It's a big tank. And what I'm going to tell you about the tank is that the height of the tank, this is a different problem here. Height of tank is twice the radius. But it's absolutely humongous. Okay, well, it's a tank. It holds water. In fact, water comes in at 8 pi cubic feet every second. So we start pumping water in. And the question is, what is the rate of change of the water level when the volume of water is 18 pi cubic feet? That's part A. And part B is a little bit different. Suppose instead that there is now a leak in the bottom. So we actually have a little leak right in the bottom. The tip is not quite closed. And I'm going to assume that the way the water pushes down is such that the more water there is in here, the faster it comes out, because the weight of the water is pushing on it. So in fact, if I can say it, suppose that the leak lets out 1 cubic feet per second of water for every cubic foot of water in the tank. Okay, so that means that, say, there are 20 cubic feet of water in the tank. Well, the leak is letting out 20 cubic feet per second. So you would think after 1 second it would all be gone. But actually it wouldn't, because when it goes down to 10, after a little bit, the rate has actually slowed down. So it takes longer than a second. And then, in fact, the slower it gets, the less water there is, the less the leak lets out. And don't forget, we have water pouring in as well against the leak. We still have 8 pi cubic feet per second. But we also have this hole. So the question now is, Now, what is, well, now redo part A under this new circumstance, i.e., what is the rate of change of the water level when the volume is 18 pi cubic feet with the hole? Okay, so it's two different questions, really, but I'm going to solve them as if it was one question. I'll do part A, and then we'll modify it to do part B. Actually. Okay. Is the question clear, at least in what it's asking? Anyone have any sort of questions about the question, as it were? Okay. So, basically, the whole height of the tank never changes. I don't know what it is, though, so I'll still have to call it something. The radius of the tank doesn't change either. But the water level changes, and we don't know exactly where it is, so we might as well let its radius be r and its height be h, whereas the height of the whole tank is capital H. We see actually, well, let's play by our rules. One is that let r be the radius of the water level, of water surface, and it's in feet. Let h be the height of water surface, i.e. the water level, in feet. Those are actually the only quantities that are changing apart from let V be the volume of water in cubic feet. So those are actually the changing quantities. I did introduce two other quantities, but I kind of want to just sort of say R and H are unchanging radius and height of the tank, respectively, in feet. So I just don't want to confuse myself with 5 variables when we really only have 3. In fact, moving on to step 2, we know... Oh, by the way, I should identify that H is the one that we're interested in, right? We want the rate of change of the water level. So H is the special variable that we're going to need to find the HDT. Basically, I just think you should, even going into step 2, start to worry about what our ultimate goal is to find the HDT in both parts of the question. All right, so step 2, we know, well, we have similar triangles here. However high the tank is, similar triangles tells us that little r over little h equals big R over big H. But actually, we knew that the height of the whole tank is twice the radius. So I don't know what these are, but I know that H is 2R. So actually, this is just 1/2. Another way of writing this is that H equals 2R. And that is one equation. Let's sort of label this. I'll label it with a star. What the hell? That's one equation relating the quantities. H and R, H is the height of the water, that's certainly changing. So is the radius of the water. But it's a pretty simple relation between them. H equals 2R. It's not enough because we've also got the volume is changing. We also know we need an equation involving the volume. And because it's a cone, we need to know the volume of a cone. 1/3 pi r squared h. You need to know that volume of a cone formula. And that I will call star star. just to really emphasize that those are the only two equations I really care about going forward. They relate h and r, and they relate v and r and h. So actually, if we know any one of those quantities, we can work out the other two by simultaneously solving those two equations. Okay? Any questions about the problem so far? Well, let's move on to step 3. Step 3 says just differentiate implicitly. So let's do both ones. For star, we have dh dt equals 2 dr dt. Nothing more to say about that. And for star star, well, we have dv dt equals 1/3 pi, and we need d dt of r squared h. This is not the only way to do this. I'll discuss another way. In fact, I think this might have been the way I did second in the book, but hey, variety is the spice of life. So, we need ddr of r squared h. And as usual, I'm going to put an equals and come back to this prickly thing after I finish the working over here. So I need ddr of, say, uv, where u is r squared and v equals h. So this is equal to v du dr plus u dv dr. Product rule. V is h, du dr is 2r, u is r squared, and dv dr is simply dh dr. So if I surgically insert this over here, I will get 1/3 pi outside of 2rh plus r squared dh dr. And that is an expression for dv dt. Now, we need to do some cleaning up. In fact, you may well prefer the other method, because you wouldn't have to use the product rule, but I'll talk about that in a second. Let's just finish off the problem. Once I get some more board space. I need like a board boy or board girl or something. You know how in tennis they have ball boys and ball girls. I need some 10-year-old kid. Well, anyway. So, let's just summarize those equations. I have dh dt equals 2 dr dt. And I have just found that dv dt is 1/3 pi 2rh plus r squared dh dr. What the hell? Who said anything about ddr? Oh man, I'm really losing the plot here. Would you please come back over here? Why didn't anyone say anything? You've got to stop me when I write stupid things like dv dt is something ddr. Where did that ddr come from, huh? Who knows where the ddr came from? Yes, you're right. It came out of my... Okay, basically, it was a mistake. It should have been ddt, which means that all this is bull. This needs to be dt. This needs to be dt. This needs to be dt. And all this is just wrong. Stop the tape. No, just kidding. We'll fix it up. We'll fix it up. We can fix this up. So what do we get? Let's just go back here. V is h. Du dt, we have to differentiate implicitly and get 2r dr dt. That's better. Plus u is r squared dh dt. So I was almost right. I just changed it just needs to be 2RH, there's an extra dr dt there, and it needs to be r squared dh dt. So now I just need to write it out correctly here. I knew something was a little fishy. 2RH dr dt plus r squared dh dt. All right, we're making some progress here. This first equation tells me I can replace dh dt by 2dr dt, rather. So this is pi over 3, 2RH dr dt plus r squared times 2 dr dt. And so actually, this whole thing is 2 pi over 3 times h, well, let's do it like this, h plus r squared, rh plus r squared dr dt. Final. Now, unfortunately, in my haste to be clever, I have not really looked at the quantity that we want. We want dh dt, not dr dt. So I'm going to just borrow the 2 dr dt again. Whoops, should have done this in the first place. Never mind, not too late. Pi over 3 rh plus r squared dh dt. See, I've replaced 2 dr dt by dh dt, which probably I should have taken this dr dt and replaced it by 1/2 dh dt. Never mind, I got out of it okay. Which path? Well, 2 dr dt is dh dt, right? What I'm just saying is I should have thought ahead and said, oh, 2 dr dt is dh dt here, and left this dh dt alone. Then everything would have been there. I would have saved myself one step, right? I'm already embarrassed enough that I screwed up the previous computation, and in fact, I did it the hard way first before I did it the easy way. I will show you the easy way soon. So this is not my finest moment. Apologies. But we'll get through it, as I said. Now, we are in good position to finish off the darn problem, at least the first part of the problem. So, what do we know? We know that dv dt, at least in part A, is equal to 8 pi. Because there's 8 pi cubic feet of water coming into this tank. Also, we want to know what happens when the height of water is... No, when the volume is 18 pi. That's what we want to know. Well, I come back to my original two equations. Again, we have h equals 2r, and we have v is equal to 1/3 pi r squared h. So when v equals 18 pi, we have 18 pi is 1/3 pi r squared h, which simplifies down to r squared h equals 3/18, which is 54. But h equals 2r. So this means we get r squared times 2r is 54. This is 2r cubed. So r cubed is 27. R equals 3. And of course, h is equal to 6 because it's 2r. So at the moment we're interested in, r is 3 and h equals 6. So come over here. When r equals 3, h equals 6, and dv dt we already know is equal to 8 pi, this equation becomes 8 pi is pi over 3, RH is 3 times 6, plus r squared is 3 squared, dh dt. So this means 8 pi is equal to pi over 3. 18 plus 9 is 27. And finally, dh dt is 8/9. And that is the first part of the question done in the hard way. So, i.e., the water level rises at 8/9 feet per, what was it, second or minute? Second. Fine. Now, you say to me, why did you go through all this work when you could have eliminated one of the variables? And the answer is, I just don't know. I don't know why I did it this way. I meant to do it this way second, but I just started doing it. So let us rewind back to the time, all the way back to when we had these two equations, star and star star, and let's try to do this a simpler way. Now, what I want to emphasize is, h is such a simple function of r that we could easily eliminate r or h, and we should. And I didn't put that in the method. Maybe that's why I continued this way. So the method could say, consolidate equations first before differentiating, if you can. But imagine this was some nastier relation between h and r, and some nastier one between vr and h, and you couldn't solve simultaneously. Then you would have to do what I just did, differentiate them both implicitly, and then solve simultaneously. But I want to redo part A using a much simpler method, and then I'll do part B very quickly after it. So I apologize for doing the more difficult thing. I could have taken this equation, h equals 2r, and written it as r is h over 2. And then in v equals 4/3 pi r squared h, I could have just replaced r by h over 2. 4/3 pi h over 2 all squared times h. In other words, v is equal to 4 over 4. So that cancels out, and we just get pi over 3h cubed. That's a little bit simpler, isn't it? Now, why did I change it to h and not to r? Well, I wasn't going to make the same mistake twice. I know that I need to find the h dt, right? That I did that all the way at the beginning. I noticed I need dh dt. R is not important. So that's the equation I want. And look how much simpler this is. I just differentiate this implicitly, and I get dv dt is pi over 3 times the derivative of h cubed is 3h squared dh dt. And this works out as pi h squared dh dt. Well, that's a little bit simpler, isn't it, than all that other mess there? But it's good to know that we can do it. dv dt is pi h squared dh dt. Again, we still need to solve when v is equal to, what was it, 18 pi? We have 18 pi is pi over 3 h cubed. And if you work this out, 3 18s are 54. So h cubed is 54. That doesn't sound right. Why is it 4/3 pi? It's a 4/3 because it's a sphere. Can't you see? It's a sphere. Okay, it's not a sphere. It's a cone. And I am just hallucinating. That's all it is. I'm sorry. There is no 4. Thank you for pointing that out, because I was starting to panic. And unfortunately, I have screwed up again. This is not my night. I might just go and hide behind this lectern. Still there. Okay. It was worth a try. Okay. So let's see. Good news is, this is now going to work out. Okay, so h cubed is 12 times 18. And I don't actually dare work out what that is. So I'm simply going to write this as, I'm going to cop out and write this as 3 by 4 by 3 squared by 2. So it's 9 times 8. So actually, no, it's not 9. It's 3 cubed times 2 cubed. So it's just 3 times 2. It's 6. Woohoo! Okay, so h is 6. That means I can come over to my equation for dv dt, which is just on the right of the board there, which I believe in its correct form is pi h squared over 12 dh dt. I know h equals 6, and I know dv dt is 8 pi. So I get 8 pi is pi times 6 squared over 12 dH dt. And it's not right. It's just not right. Nothing is working out here. Now I forgot a 3. Where did I forget the 3? Yeah, I mean, look, what the hell's going on here? I forgot the 3. I mean, there was a 4, and then it was a 12, and of course, 3 over 12 is 4. I should just give up right now. I mean, come on, if I can't get this right, I don't know what's going on. I am ashamed. I am very ashamed of myself. How much time left? This was supposed to be so professional. I hope you're enjoying yourselves. Okay, so anyway, basically, if you work this out, you get 36 over 4 is 9, and hallelujah, dH dt is equal to 8/9 once again. Okay, let's just take some stock. If I had done this correctly, I would have written down the correct equation for V, and then replaced R by H over 2. Here it is. Then you simplify this thing, and you get V is pi over 12 h cubed. Now you differentiate it properly, and you get pi h squared over 4 dH dt is dV dt. You solve V equals 18 pi. That allows you to find h. And then you come back into the dV dt equation, plug in the value you know for dV dt, and the value you've just worked out for h, and that allows you to find dH dt. Fan-bloody-tastic. Now, we still have to do the second part, and I am not even going to dare to try to pull down the top board, because the way I'm going, it will probably just fall on my head. Actually, maybe that's the preferable option, but never mind. I want to just do the second part of the problem, which said that there's now a leak, and the leak is letting out 1 cubic foot of water per second for every cubic foot of water that is in the tank. Now, the good news is we actually don't have to do anything to change what we had, because everything is still the same up until the point where dV dt is, and can I even copy this directly? Pi h squared over 4 dH dt. That is still true. As is, of course, V equals pi over 12 h cubed. This is still true. This is still true. It's still a cone. And the cone has a certain shape. The only reason there's no R is because of the shape of the cone. So this is true no matter what. The difference is that we now are not going to replace dV dt by 8 pi, which it was in the first part. We need to put the leak in somehow as well. So basically, what should dV dt be? Well, it should be the inflow minus the outflow rates. Inflow rate minus the outflow rate. Right? The volume changes by, well, what comes in minus what goes out, that rate. Okay. Question?
Why V equals pi over 12 h
Cubed.
Where do you bring it from?
Oh, I brought it from the other part of the board, and I really screwed it up over there. But basically, it's the volume of a cone of height h when the radius is half the height, which it is no matter what the water surface looks like. I mean, it's a small copy of the whole tank. Okay, so what's the inflow rate? Well, we still have 8 pi coming in. How about the outflow rate? Well, the outflow rate, remember, this is 1 cubic foot per second for every cubic foot in the tank. So how many cubic feet are in the tank? Well, V. So we have 1 V. The bigger V is, that's the more you have in the tank, the more is leaking out. The idea is that, as I said, the weight of the water pressing on it is forcing more through the leak. I don't know if that's physically accurate. But in any case, that's now the expression for dV dt. Instead of 8 pi, we have 8 pi minus v. And the problem says, well, let's plug this in. When the volume is 18 pi, we already know that h equals 6. So what is dV dt, though? dV dt is 8 pi minus v, which is 8 pi minus 18 pi, because that's how much water is in there. So it's minus 10 pi. So actually, when the volume happens to be 18 pi, which is what we're considering, the outflow rate by the leak is bigger than the inflow rate. We're pumping in 8 pi, but the rate at that instant of time is 18 pi. Now, of course, as the water level goes down, the leak starts dripping slower, and now it might actually increase. But at the moment, dV dt is minus 10 pi. The fact that it's negative means that the water in the tank is actually getting smaller. More is coming out than is going in. Anyway, we can now finish the problem back in this equation here, but this time with dV dt as minus 10 pi equals pi, h is 6, over 4 dh dt. And the difference now is that dh dt, 36 over 4 is 9, so now dh dt equals minus 10 over 9. So that means water is flowing out of the tank at a rate of 10⁹ feet cubed per second, at least at the instant the volume is 18 pi cubic feet. I've squished this down there, but that basically says at the instant the volume is 18 pi cubic feet, water is flowing out of the tank at 10⁹ cubic feet per second. Right? Remember, it's a different rate at different times, as different as the volume changes. So all I'm asking for is what, at that snapshot of time, how fast is the water? You could come back later, it will be a completely different speed, but at that moment, what's the rate? And, yeah, a question.
Pi 6 squared over 4.
Yes. Well, this time I think I actually did it correctly. 6 squared is 36, divided by 4 is 9, and then I get 10⁹. So I think that one computation is correct. I had said that I was going to ask for other rates questions, thinking I would finish this about 10 minutes ago, but because I screwed up so badly, we are basically out of time. I guess I have time for one more question about this example, if anyone has one. Otherwise, I think that I'd better just, anyone have any questions about this? I just want to point out that Part B was not that hard, even though it looked hard. We actually used all the stuff we'd done for Part A. We just had to change the value of dV dt. Otherwise, there's no difference. Any other questions about it, just quickly? Okay, well, as far as we're concerned on the videos then, next time we'll continue with exponentials. And as far as we're concerned in the room, well, I'll tell you about that in a few seconds.